In chapter 15, we will be looking at substitution reactions. This time we'll be looking at substitution reactions at sp3 carbons. So in this presentation, before we actually look into the actual substitution reaction, we'll cover some terms. The first term that we'll define will be electrophiles. So we'll define electrophiles and give you examples of electrophiles. Then we'll look at leaving groups and give you examples of leaving groups, and also nucleophiles. We'll define these terms and give examples. Then we will look at applying those terms to reactions that are substitution reactions. Next, we'll look at the mechanism. Of course, as you know, when two reactants are mixed, they do not just magically form the products. They go through different steps before they actually form the product. And that's the mechanism, which is a step-by-step description of a reaction, typically described by using arrows to indicate electron movement. So we'll look at one mechanism. It's called the SN2 for substitution bimolecular. That's why that 2 is there. Then we will look at features of the SN2 reactions. There are certain characteristics that go with an SN2 reaction, so we will examine that. Then lastly, we look at the application of substitution reaction to synthesis. Of course, as you know, synthesis is a very important aspect of organic chemistry, so we'll utilize the concepts learned in substitution reactions to synthesis. Okay, so let's begin. The first term that we'll need to define here is electrophile. So of course, as you know, the term phile really means loving. So an electrophile is an electron-loving species, electron-loving. Of course, as you know, electrons are negative, so electrophiles are positive or partially positive. So you should be able to look at a molecule and determine if it's an electrophile, and even more specifically, what is the electrophilic region of that molecule. We'll use that information to predict reactions. So let's look at these molecules. This one is acetone. As you can see here, this is a double bond right here from carbon to oxygen. As you know, oxygen is more electronegative than carbon. So the electrons in this covalent bond are closer to the oxygen than to the carbon. Of course, you may recall we described that as a polar covalent bond. So it's a polar bond, 2 poles. As you can see here, this carbon is partially positive. Therefore, it is the electrophilic atom for this molecule. You should be able to identify the electrophilic atoms for molecules because you will use that information to predict the reactivity. Here's another molecule. This one has a bromine. Of course, as you know, bromine is more electronegative than carbon. So this single bond is also described as a polar covalent bond, which means that this carbon here is partially positive and the bromine is, as expected, partially negative because it is electronegative. As a result, this carbon is partially positive. Here's a carbocation. As you can imagine, it is fully charged, so it has a fully positive charge, so therefore it is a very good electrophile. Let's look at DMSO. This time carbon is bonded to sulfur. Sulfur is more electronegative than carbon. So as you'd expect, this carbon here is the electrophilic atom for this molecule. Let's look at this one. This bond here is a polar covalent bond because this carbon is bonded to oxygen. Oxygen is very electronegative. So therefore this oxygen here is partially negative and this carbon is partially positive, making this carbon the electrophilic carbon. Same for this molecule. This molecule we use quite a bit in our synthesis. But again, to concentrate on this atom, it is bonded to an electronegative chlorine, another electronegative chlorine, and an electronegative oxygen. So as you can expect, that sulfur is very electrophilic. And you can imagine it's a very reactive molecule because this sulfur is very, very electrophilic. So we'll use that quite a bit in our synthesis to make different molecules. Okay, let us concentrate now on looking at features of the electrophile, the actual molecule. And we'll look at leaving groups here. So let us look at this molecule where X here is the electronegative atom which makes this bond a polar covalent bond. And this carbon is the electrophilic atom. This group here is typically electronegative, and as you can see here, if this bond breaks in a heterolytic manner, hetero here means 2 electrons will go to 1 atom. As you can imagine, X here being very electronegative would take the electrons as shown here. So what's left behind is a carbocation. So let me do that again. So we have a molecule like this, where this is the electrophilic atom and this is the electronegative atom, such as bromine or a halogen. It's possible for this bond to break. This time this bond will break in a heterolytic fashion, not homolytic, as we've seen before with the free radicals, but in a heterolytic manner because one atom here is more electronegative and will pull these electrons as indicated with that arrow when it's broken. What's left behind is a fully carbocation, positive. So that's important as we look at some reactions here, or potential reactions. Let us look at this one, alkyl halide. So we have a halogen here, in this case iodide, bonded to carbon. Iodine is more electronegative than carbon. So this is a polar covalent bond right here. It can break heterolytically, where these electrons here go to the iodide to form the iodide anion. As you will recall, the iodide anion is very stable. Okay, so that bond breaks readily because it gives a very good iodide anion. In general, we call this group here a leaving group. So a leaving group by definition is a group that after the heterolytic cleavage, what's formed is a very stable anion. A very stable anion. Because why anion? Because it's going to take the bonding electrons. And what's left behind is, in this case, a carbocation. Let's look at this one. This is a bromide, by the way. I'll correct that. For an alkyl bromide, which is also electronegative, if this bond is broken, as shown with this arrow, it gives here the bromide anion, which is a good leaving group, which is also stable. How do you know it's stable? because, as you know from the acid-base chemistry, the conjugate base of a strong acid is stable. So the conjugate base of HBr, conjugate acid of HBr, of Br negative is HBr. Let me say that again. The conjugate acid of Br negative is HBr. And HBr is a very strong acid, of course, as you know, which means that its conjugate base here is very weak, which means that it's a good leaving group because it's very stable. It can accommodate the negative charge. Let's look at some more examples. Here is one example here. So let's look at this bond. It's bonded to this carbon, and it's an oxygen, electronegative, so therefore this carbon here is the electrophilic carbon. If this bond breaks, as shown by this arrow, it puts the electrons, notice 2 electrons, onto the oxygen. The question now is this species here stable or not? It is stable due to resonance. That's the acetate anion. So once these electrons come in to form a double bond here, these electrons kick out to put the electrons on the oxygen. So by resonance, this species here, the acetate anion, is stable. What that means is that this bond is a weak bond and breaks readily. So when we start doing reactions, you'd expect that this type molecule is very reactive. Here's another molecule shown here. So this is the electrophilic atom carbon. Why? Because it's bonded to oxygen, which is electronegative. If this bond breaks, as indicated with that arrow, it would put the electrons on the oxygen. This is very stable, as you can imagine, because we can delocalize the electrons into the other oxygens that's bonded to sulfur. This group is known as the tosylate group or the OTS group. So, conclusion. This bond here is weak because if broken in a heterolytic manner, it gives a very good leaving group which is stabilized by resonance and of course a carbocation. As another example, let us look here at the OH. So here's the electrophilic atom. Here is oxygen. So therefore this bond here is the polar covalent bond. So if we had to break that bond in a heterolytic manner, we put the electrons onto the OH group. Of course, as you know, the OH negative, which I'm drawing here, is a strong base. So therefore, it is not a good leaving group. So even though this bond is a polar covalent bond, making this carbon electrophilic, this is not a good leaving group because after it has left, if it could, it would be OH negative, not a good leaving group because it is a strong conjugate base, not stable. So what can be done, however, is to protonate it to get an intermediate looking like this. Now you can see if we break this bond, putting the electrons onto the oxygen, what we have here is water. Water is an extremely good leaving group. Why? Because it's a weak conjugate base. We know it's weak because we ingest it every day and there is no problem in terms of major reactions. So this is a weak conjugate base here, and of course we have a carbocation left behind. So bottom line is, if we have a poor leaving group such as the OH, let me clear that so you can see it. If we have a poor leaving group such as the OH, this bond will not readily break. Well, notice, will not readily break even though it is a polar covalent bond. But if we protonate that to convert it to a better leaving group, it will now break to give water as the leaving group and a carbocation. Same here, having amine. Amine is not a good leaving group, as you can expect, because if we did that, what we would get is negative and CH3 here and CH3 here. That's the amide anion. Very strong because its conjugate acid is ammonia. So this is again not a good leaving group. So look out for that. If you have a group that's not a good leaving group, the reactivity is reduced. But we can convert it to a good leaving group using an acid-base reaction as shown here. So now the leaving group becomes an amine, and of course an amine is a pretty stable conjugate base, leaving behind a carbocation which can react further. So conclusion from this overhead here is that if we have poor leaving groups such as OH or an amine, the reactivity is reduced in terms of substitution reactions, but we can convert them to a good leaving group by protonation to get a stable conjugate base such as an amine or water as the leaving group. Okay, let us look at another terminology before we start looking at reactions. This time we'll look at nucleophiles. As you can imagine, here's an important aspect here, phile, loving. This time it's nucleus loving. Of course, as you know, the nucleus is positive, so therefore it's a nucleus loving species or a positive loving species. Now you can get a good feel as to the type reactions we will be discussing. Because if you have a nucleophile which loves a positive species, and you have an electrophile which loves a negative species, that's a good combination for a reaction to occur. So for a nucleophile, they must have at least one unshared pair of electrons. Notice, keyword electrons, at least one pair, and that's the key, is a pair. As you will recall, that's the same definition as a Lewis base, isn't it? The Lewis base is a electron pair donor. So Lewis base is a synonym for a nucleophile. So here's a general example of a nucleophile. We represent it as Nu, but here is one unshared pair. Keyword here is pair of electrons. We could also see a nucleophile as an ionic compound, such as M being the cation, and here the nucleophile is the anion. So this is the nucleophilic region or portion of this ionic compound. Let us look at some examples. Water is a nucleophile because it has at least one unshared pair of electrons, and this atom here, the oxygen, is the nucleophilic atom. Let's look at ammonia. Here's a pair of electrons, and this atom is the nucleophilic atom. You'll see why I'm emphasizing the nucleophilic atom in a second. Let's look at another example, potassium hydroxide. This time it's a salt, where the potassium is the cation and the hydroxide here is the anion, where it has at least one unshared pair of electrons, and the oxygen is the nucleophilic atom. The reason why I'm emphasizing nucleophilic atom is because I emphasized the electrophilic atom in the previous slides. So as you can imagine, the nucleophilic atom will react with the electrophilic atom. So let's apply that. So here's a general substitution reaction. We have the nucleophile, which we'll write here. Here's the unshared pair of electrons. The electrophile we'll write like this. This is the leaving group this time. And here is our electrophilic atom. The substitution reaction involves this nucleophile with its pair of electrons bonding right here, and this leaving group taking its pair of electrons to form here a good leaving group. So once again, just to emphasize, this is the substitution reaction here that we'll be looking at. It involves a nucleophile with a, let me clear this so you can see exactly what we are making reference to here. So this is the nucleophile with its pair of electrons, and here are those pair of electrons, and here's the Nu atom, and here it is. Here is the electrophilic carbon, and here's the leaving group. This bond will break, and the leaving group will take those electrons to form a good leaving group. How do we define a good leaving group? One that is stable. And we have formed here a new bond to this carbon, and that's called the organic product, or the product of the substitution reaction. Let's apply that concept. So let's look here at chloroethane. Let's analyze that, because what you'll see is just chloroethane written. But let's analyze it. Now you can see why it's best to draw out the structures of molecules so you can make your observations. The first observation is that this carbon is bonded to an electronegative chlorine, which makes this C-Cl bond a polar covalent bond, which means that this carbon here is electrophilic, and this is our leaving group. Let's look at this molecule. This molecule here is the hydroxide anion. It has at least one unshared pair of electrons as indicated here. Therefore, it is a nucleophile. In this case, the oxygen is the nucleophilic atom, and in this case, the carbon is the electrophilic atom. So if a reaction occurs as a substitution reaction, we'd expect this oxygen to bond to this carbon as shown here. Notice that these electrons are right here, and this chlorine actually takes those bonding electrons, as I should have included 2 electrons here. So that's how you'll predict your substitution organic product. So when we do synthesis, you'll start with a molecule like this, and you'll synthesize a molecule like that. This is a chloroalkane, and this is an alcohol. Let's apply that to some more examples. So here is our reactant, carbon, chlorine, partially positive, electrophilic atom right here, leaving group, nucleophile, nucleophilic atom. So we should get a substitution reaction in which we form a new OC bond. Of course, the chlorine comes off with one of these hydrogens to form HCl as the inorganic product. Let's look at this one. Bromine, good leaving group. This bond is a polar covalent bond, which means that this carbon is partially positive, or the electrophilic carbon. This is a salt, as you can see here, cation and anion. Here is a pair of electrons. So as you can imagine, this sulfur is the nucleophilic atom. So it will form a bond to the carbon in the form of SH. Notice the entire group is coming along, but the bond is really made to this sulfur. And of course the bromine is bonded to the bromine comes off as a bromide and forms a salt with the sodium cation to form sodium bromide. Last example. Look at this molecule. I'll just point out the highlights here. Here is our electrophilic atom. Here's our leaving group. Here is our nucleophile. Written a little tricky here because it has an unshared pair of electrons bonded to the carbon of the cyano group. It's actually C triple bond N, electrons, negative, and of course Na plus. So it's ionic. But the bottom line is this carbon here is the nucleophilic carbon of the cyanide salt. So as you expect, you'd form a bond between this carbon of the cyanide bonded to this electrophilic carbon of the electrophile. So this is your organic product, and the inorganic product, as you can imagine, is the sodium bonded to the chlorine to form sodium chloride. Let us make sure you have it. So let us work these problems out. So the problem is to, wherever there's a question mark, write the organic product or the organic reactant. So let's see. So you have to do the observation and the analysis. Remember, organic chemistry is not a course of memorization. It's a course of applying the concepts that we have fully understood. So let us apply the observation first on this molecule. Here's a carbon, here's a bromine. Good leaving group, electrophilic carbon. Here's ammonia. Notice a lot of times we do not put the non-bonding electrons on molecules because we assume you remember your general chemistry and you know that ammonia has an unshared pair of a pair of unshared electrons. So this would be our nucleophile, this would be our nucleophilic atom. So this nitrogen is now should bond to this carbon to form the product. Here's another example. Here we don't know what the electrophile is, but obviously it is an electrophile since we have here potassium hydroxide, which has at least one unshared pair of electrons. Remember, this is OH negative and K plus. And the OH negative has at least one unshared pair of electrons. So this OH here will bond to a carbon to form this bond. So we can now write the reactant here, which should look pretty much like this, except it has a leaving group. What is that leaving group? More than likely it's a chlorine, because you can tell from the inorganic product. Let's look at this one. This one is asking you for the nucleophile, because we recognize this as the electrophile, where this is the electrophilic carbon. This is our leaving group as shown here, and of course it has a sodium, so more than likely this is a salt. And of course here is our new bond, which came from the nucleophile. Lastly, we have a similar example here, electrophile, nucleophile, new bond right here. So what is this? More than likely it's associated with this. So you just have to come up with the correct structure for the nucleophile. Let's see what the answers are. So as you can imagine, this is here. So this is our nucleophile right here. This is our leaving group, and this will form a bond right to that carbon, and here it is. Here's another example. This is our nucleophile, a salt. It will bond to an atom. So let's do the analysis. So this is our product. So we know that on this carbon we had a leaving group. So here it is. And it's a chlorine because it's in the product. Here's another example. This is our electrophile, and we have this as a product. So therefore this new bond is formed from our nucleophile bonding to this carbon, and this bromine comes off as the salt. Same thing here. This is our KCN. Notice it's a salt because K plus is very electropositive, and so it is bonded to a anion. And this has 2 electrons, as I pointed out earlier. So the bond would be this carbon bonded to this carbon as shown here. So you should be able to predict the products and reactions for substitution reactions. Let's turn our attention now to the mechanism. The mechanism, of course, as we have said before, is a step-by-step description of a reaction. As I mentioned, if you mix the nucleophile and the electrophile in a beaker, they just do not magically come together to form the product. Let's see what happens. The nucleophile, or the electrons of the nucleophile, must come in and literally get close to that carbon, electrophilic carbon, and literally push out the leaving group. So we define this as pushing out the leaving group. Key word here is this nucleophile must get close to this electrophilic carbon, and this leaves. This is the mechanism, one step in this case. So it's called a concerted mechanism. So here is the transition state where this nucleophile is literally approaching. So here's a partial bond, the bond that's being formed, and this bond is being broken as shown here by dotted lines, and that's called the transition state. After the transition state is formed, we form the product with a new bond, and this leaves as a leaving group. So once again, the nucleophile must come in and attack the electrophilic carbon, and the bromine leaves to form the leaving group and our organic product in one step. Of course, as you know, another way of representing a reaction mechanism is using the energy profile diagram. So we start here with our reactants, the electrophile and the nucleophile, go to our transition state where the bonds are partially broken and partially formed, and then once that's formed, it quickly goes on to the products, which would be, of course, the leaving group and the organic product. Notice again, this is the energy of activation. So if this is pretty large, it's a slow reaction. If this is pretty small, it's a fast or favorable SN2 reaction. By the way, the reason why it's called SN2 is it's bimolecular. So let's go back to this here. It's bimolecular because one reactant, 2 reactants take place in this very important one-step reaction. So it's an substitution, nucleophilic, bimolecular. That's why it's called an SN2 reaction. And this is the energy profile for the SN2 reaction. One transition state, and of course a concerted or one-step reaction. Okay, let's turn our attention now to aspects of the SN2 reaction. So, as you can imagine, the nucleophile must gain access to the electrophilic carbon here. To gain access to that electrophilic carbon, if we have hydrogens here, which are pretty small, there is easy access. So you'd expect this type of reaction to be fast. Or, stated differently, the energy of activation for this reaction is low. Let's look at the opposite. If the groups that are bonded to the electrophilic carbon are alkyl groups, such as a methyl group, another methyl group, and a third methyl group, making it a tertiary carbon. Remember that methyl groups are much larger than hydrogens. So therefore this is a very, I'll even use it again, very slow reaction. As a matter of fact, it's considered not to react by the SN2 mechanism because the nucleophile just cannot get access to this carbon in a tertiary electrophile. So, a conclusion. The order of reactivity of the electrophiles in an SN2 reaction is the methyl is more reactive than the primary, than the secondary, and the tertiary is so crowded that it's considered not to react by the SN2 mechanism. So again, you need to be able to identify a methyl electrophile, and if it's different from a primary electrophile or a secondary electrophile, the methyl will react the fastest with a nucleophile. So let us apply that knowledge or those concepts. So looking at these electrophiles, these are electrophiles because we have here chlorine and chlorine, a good leaving group. Chlorine, chlorine, good leaving group, and the same here and here. So what we need to determine now is, of these two electrophiles, which is a primary, which is a secondary, which is a methyl, and which is a tertiary, and apply that knowledge that we have just gained. This chloride is a secondary. Why? Because it's bonded to 1 and 2 alkyl groups. This chloride is primary because it's bonded to just 1 alkyl group. So therefore, this is the faster or the more reactive chloride. Let's look at this. This is a tertiary chloride. Why? Carbon here that has the chlorine is bonded to 1, 2, and 3 alkyl groups tertiary. This is a secondary which is bonded to 1 and 2. So therefore this is more reactive by the SN2 mechanism. Let's look at this one. This is a secondary and this is a methyl, as you can imagine. So therefore this is now more reactive by the SN2 mechanism. Lastly, this chloride is a tertiary chloride because this carbon that contains the halogen is bonded to 1, 2, and 3 alkyl groups. This carbon that contains the leaving group here is bonded to 3 hydrogens and no carbon. It's a methyl chloride, so therefore more reactive. So when you start doing reactivity by the SN2 mechanism, remember the order of reactivity. Conversely, as you can imagine, by an SN2 reaction, the nucleophile must be small to gain access to the electrophilic carbon. So here's the size trend, or the trend in size for electrophiles. You need not memorize this, but just remember a small nucleophile, an example here is this, is more reactive by the SN2 mechanism because it needs to gain access to the electrophilic carbon compared to a very large nucleophile such as water. So that's the trend. So again, the reactivity for SN2 reaction is the electrophile must be primary, well, methyl or primary or secondary, but never tertiary, and the nucleophile must be small. Okay, so let us look at some bases, some nucleophiles here. You may recall when we did elimination reaction, we used this bulky base, potassium butoxide, and another bulky base, LDA. Notice they are Lewis bases because at least it has one unshared pair of electrons. Notice they're also nucleophiles because of the same unshared pair of electrons. But they are pretty bulky, as you can see here. So they are not good nucleophiles for SN2 reactions. And that's why they're used primarily for elimination reactions to give the less substituted alkenes. So you will never want to use potassium butoxide or LDA as your nucleophile. Never want to do that. Too bulky and it's too strong a base. Let's look at another concept here regarding the nucleophile. So here is a nucleophile, F minus. So let's put in the electrons. So if you look at the periodic table, you can see that F minus is to the right, is very electronegative, which means that it's very small, which implies that it should be a very good nucleophile. And it is a good nucleophile because it is very small. However, if we should put this very small F minus, the fluoride anion, in a solvent such as methanol, the effective size of that nucleophile gets pretty large because of solvation. Let's explain that concept. Methanol here is a polar protic solvent. So it's polar because of this polar covalent bond, oxygen being electronegative and hydrogen being electropositive, makes this a polar covalent bond. And of course, as you know, methanol is polar molecule. In addition, this hydrogen is behaving as a proton. So we say it's protic. Remember, proton here is a hydrogen without its electrons, So this is called a protic solvent. So this is a protic polar POLAR solvent. So if we should put the fluoride anion, which is very small, in a polar protic solvent such as methanol or water, the effective size of this fluoride gets pretty large because it's carrying with it a lot of solvent molecules that bond to the electrons. So the size of the nucleophile is dictated by the solvent. Let me state it differently. The effective size of the nucleophile is dictated by the solvent. If we should put this very small fluoride anion in a protic polar solvent, its effective size is no longer small but very large, and hence it's not a good nucleophile in these solvents. So we'll have to exercise extreme care in the solvents that we use for the SN2 reaction. We have to make sure that it is not a polar protic solvent. In other words, it should be an aprotic solvent. Aprotic does not have a hydrogen that's bonded to an electronegative atom, such as oxygen. Here are some solvents that are extremely good for SN2 reactions. Acetone. Notice the hydrogens are bonded to carbon. DMSO, dimethyl sulfoxide. Notice again the hydrogens are bonded to carbon. Diethyl ether. Again, the hydrogens are bonded to carbon. And of course, tetrahydrofuran, THF, the hydrogens here are bonded to carbons. So these are considered polar aprotic. The key word here is aprotic solvents that are used for SN2 reactions. So now you can see, whenever you set up your reactions to go by SN2, and I ask for reaction conditions, you cannot use methanol or water as your solvent. We'll take off points for that, because it will make the nucleophile very large, effectively larger than it really is, and of course that cuts down on the reactivity of SN2 reactions. Let us look at another aspect of SN2 reaction. So as we said, the nucleophile must gain access to the electrophilic carbon and push out the leaving group. It turns out that if this carbon here is chiral, or has 4 different groups around that carbon, there is an inversion of configuration. So if this is R, this is going to be S. There's an inversion. It literally flips. What you'll see written in most books is like on a rainy, windy day, you have your umbrella, and it's really windy, the umbrella flips. So the inversion of stereochemistry. There's an inversion of stereochemistry for SN2 reaction. So here's the reaction. Nucleophile reacting with an electrophilic carbon. Here's a leaving group over here with, of course, 2 electrons. And there is an inversion of configuration of this chiral carbon to give an inverted chiral carbon in the product. Here's another example. This carbon is chiral. Here's our leaving group. This carbon is also electrophilic. Here's our nucleophile. In a solvent, notice the solvent now is important, DMSO. In DMSO as a solvent, we'll have a substitution reaction, but now we'll have an inversion of configuration. So this is in the front, and now the product, nucleophile, is in the back. Let us look at an example here. Very interesting one. Because here we have our electrophilic carbon bonded to oxygen, and it's an OH. As we said, the OH is a very poor leaving group. We can convert the OH to a good leaving group by reacting it with a compound called tosyl chloride. Here's the structure. But the key here is that the tosyl chloride will react and just remove that hydrogen to form this now as a good leaving group. So this becomes our leaving group. So this reaction here does not change the stereochemistry because the reaction does not occur at the chiral carbon. So this is not a substitution reaction, not an SN2 reaction. This reaction, however, is an SN2 reaction where this is now our nucleophile, and it is coming in from the rear and kicking that out to get our product here, which is an inversion of configuration. We'll use that strategy quite a bit. If we have a poor leaving group and we need to retain the configuration and convert it to a good leaving group, we can use that strategy, and then we perform the SN2 reaction to get inversion. But I'll say more later on. So in summary, for the SN2 reaction, the electrophile, the reactivity of the electrophile is the primary, or the methyl is more reactive than the primary and more reactive than the secondary, and we literally not use a tertiary halide or tertiary electrophile for an SN2 reaction. Stereochemistry. There is an inversion of stereochemistry. The nucleophile must be small and a weak base. Notice we said that the strong base such as LDA and bulky bases typically do not work. Well, do not work, period. And leaving group must be good leaving group. We said that earlier, such as your bromide, large bulky group, or if it's stabilized by a resonance, must be weak conjugate base. The solvent must be non-ionizing, and more specifically non-protic or aprotic solvent. So please do not use water or methanol or alcohol as your solvent for your SN2 reaction. The mechanism is bimolecular. Why bimolecular? Because two reactants, the electrophile and the nucleophile, come together in one step. We call a concerted reaction to produce the product. Lastly, let's do an application and then we conclude. So we'll now combine most of the concepts that we've learned from previous chapters, including substitution reaction. So let's see, how do we transform 2-methylbutane into this target molecule? So in other words, we have lots of this molecule here as our starting material, and you need this molecule as your product. How do you make it? What are the steps that we put here? So as I said, you can't memorize your way through organic chemistry. You'll have to perform observations and critical thinking and apply the concepts that we have learned. So let's do that. Let's do the observations and retrosynthesis strategy. Retro here means working backwards. So let's work backwards, starting from the target molecule. First thing we observe is the CN. And we recall that we can introduce CN into a molecule if we had this CN negative as a nucleophile. So we can introduce that through a SN2 reaction. So now we have to select the appropriate solvent and the nucleophile. But to have that happen, we need a good leaving group bonded to this carbon. We need a good leaving group. So we can think of good leaving groups. The question now is, if we have a good leaving group, how can we introduce it here? One way of introducing it here is if we had an alkene functionality, we can do an anti-Markovnikov addition to add a leaving group here, such as a bromide. And of course, as we know, bromide is a good leaving group. And then, of course, how do we go from this molecule to this molecule? You've done that. That's one of your tutorial questions. We'll have selective bromination, and then we'll have elimination to get the alkene. And again, for this type elimination, notice this is the less substituted double bond, which means special conditions for that elimination, which of course, as you may recall, require a bulky base. So let's see. So let's apply that strategy and those observations. So if we had this, let's start over here now that we have the strategy in place. Let's start with this molecule. Here is a hydrogen, and it's a tertiary hydrogen, and we can substitute that for bromine with a free radical substitution using bromine because it is more selective. Notice you will not use chlorine because chlorine is not selective for the tertiary, the weaker CH bond. Bromine is. Once we have this, we can do elimination, special type elimination with LDA, very bulky base, to get the less substituted double bond right here. Once we have this double bond here, we can do an anti-Markovnikov addition of HBr. Don't forget those reactions in which we have HBr in peroxide and heat to give this as a product. Now we have introduced Br as a good leaving group, and we can now have a substitution of KCN right here, kicking out the bromine to get our target molecule. Let me emphasize again, the solvent is important. So when we do these reactions, now we need to get more specific with our reaction conditions. I think this is the last slide, and yes it is. So this is the first lecture of chapter 15, which covers SN2 reactions. I think this is all we'll cover for the exam on Thursday, which is scheduled for February 11th. I'll put out another video on the last part of chapter 15, which covers SN1, but that will be covered on the next midterm. So even though I may put it out before the exam, you can read up on it, but it will be on the next quiz and exam. So continue to study hard. This first lecture for chapter 15 is pretty involved, so you may have to look at it a couple times and slow down the video and stop at different points and get your textbook and read along and follow and work problems. But it's doable. It requires lots of thinking, lots of observation, and equally important, the applications of these concepts. So continue to study hard, and we'll have our we'll have an exam coming up next Thursday, February 11th. Okay? Bye.